In the world of robotics, some of the absolute biggest challenges are hiding behind the simplest questions. And today, we're going to tackle one of the most fundamental concepts out there, something that's both beautifully elegant and incredibly powerful.
Seriously, think about that for a second. How do you actually command a robot arm, with all of its spinning, rotating joints, to move its hand in a perfectly straight line from point A to point B? It's not as easy as just telling it to move forward, not even close.
And this slide right here gets to the very heart of the problem. We, the programmers, can only directly control the motors at each joint. We can tell them how fast to turn. We're speaking the language of angles, theta 1, theta 2. But the actual job we want the robot to do, like welding a perfect seam or picking up a package, that happens out here, at the robot's hand, in the world we understand, the world of X and Y coordinates. So there's this huge disconnect between what we can say and what we actually want the robot to do.
Okay, so here's our game plan for this explainer. First, we'll really dig into the control problem itself. Then, we'll explore these two totally different worlds a robot has to live in. After that, we'll introduce our hero, the Jacobian, see what happens when it breaks down, and finally, we'll uncover its secret superpower that has to do with forces. Sound good? Let's go. All right, Section 1, the robot control problem. The easiest way to think about this is like a language barrier. The robot's motors and the real world, they just don't speak the same language.
This slide lays it out perfectly. Over here on the left, you've got joint space. That's the robot's native tongue. It thinks in terms of joint angles. It's how the motors physically move, but for us humans, it's pretty abstract and hard to visualize. Then, on the right, you have Cartesian space, the language of the physical world, X, Y, Z coordinates. This is totally intuitive for us. It's where the work actually gets done. The whole problem is that the robot has no idea what move 10 centimeters forward means. It only understands turn your shoulder joint by this many degrees.
So what we desperately need is a bridge, something to connect these two worlds, a way to translate our simple, intuitive commands into the language the robot's motors can actually understand and execute. We need a universal translator. And that brings us right to Section 2, and the star of our show, the Jacobian. This is our motion translator. This is the mathematical key that's going to let us finally bridge that gap.
So what exactly is this thing? Okay, the formal definition is a bit of a mouthful. A time-varying matrix of partial derivatives. Yeah, don't worry about that for now. Just think of it like this. The Jacobian is basically a dynamic cheat sheet. For any exact pose the robot is in, at any given instant, it tells you precisely how a tiny little nudge of each joint motor will move the robot's hand.
And this is the magic right here. Forget all the other complicated math on the page and just look at this one beautiful core equation. It is so elegant. It simply says the velocity of the hand, which is what we want, is equal to the Jacobian matrix multiplied by the speed of the joints, which is what we can control. That's it. This is our translator in action.
To put it another way, like our source material does, the Jacobian provides an instantaneous linear relationship between the joint rates and the velocity of the tip of the arm. Now, instantaneous is the really crucial word here. This cheat sheet, the Jacobian, it's constantly changing depending on the robot's pose. But at any given moment, it gives you the exact recipe to move the joints to get the precise hand velocity you're looking for.
But as powerful as this translator is, it's not foolproof. It's not perfect. There are certain times when the translation just, well, it breaks. And this brings us to Section 3, when robots get stuck. This failure has a name. It's called a singularity. A singularity is just a specific posture where the robot basically loses its ability to move in a certain way. It loses a degree of freedom. In the math world, this means the Jacobian matrix just kind of breaks. It becomes impossible to solve our equation. But in the real world, it means there are some directions the robot's hands simply cannot move, no matter what you tell the joints to do. This slide is the perfect illustration of the most common type of singularity. When this little robot arm is stretched out completely straight, it's in a singular pose. Sure, it can still move its hand from side to side in a big arc, but it is physically impossible for it to move any further straight out. It's basically hit an invisible wall. And at that exact point, our Jacobian translator totally fails. Any command to move further out results in a mathematical error, which is exactly why avoiding these singularities is so critical for smooth, predictable robot motion.
And what's really interesting is that these stuck points don't just happen at the very edge of the robot's reach. The one we just saw, that's called a workspace boundary singularity. But you can also have workspace interior singularities, which can pop up right in the middle of the robot's work area. This usually happens when two or more of the robot's joints happen to line up in just the wrong way, and boom, you've lost the ability to move in a certain direction again.
But the story of the Jacobian doesn't stop with motion and getting stuck. It turns out it has a hidden talent, a secret power. Which brings us to section 4, the secret power of forces, and this idea that the Jacobian is actually bilingual. So up to this point, we've only talked about translating motion and velocity. But robots don't just float around in space, right? They interact with the world. They push things, they pull things, they lift things. So the next big question is, how do we translate a desired force at the hand into the correct torque for the motors?
Take a look at this diagram. If we want the robot's hand to apply a specific amount of force, we'll call it F, to some object, how much twisting force, or torque, which we call tau, does each motor way back at the joints need to generate? You know they're related, but how? And the answer reveals this incredible, beautiful mathematical symmetry. On the left, that's our original velocity equation, and on the right, that's the force equation. The motor torques you need are equal to the transpose of the Jacobian multiplied by the hand force. And transpose is just a fancy word for swapping the matrix's rows and columns. It's almost the exact same equation. The very same mathematical tool that translates motion in one direction translates force in the other. It's amazing.
And that is the huge revelation here. The Jacobian isn't just a motion translator. It's a motion and force translator. This one single mathematical tool lets us control both how a robot moves through space and how it physically interacts with its environment, all inside one incredibly elegant framework.
All right, let's bring it all home in our final section, the key takeaways. You know, we've been calling the Jacobian a translator, but I think a better analogy is the Rosetta Stone. It unlocked a whole new way of communicating. So, let's recap the journey. First, we started with the problem. We can only talk to the joint motors, but we want to command the robot's hand in the real world. This created two different worlds of languages, the robot's native joint space and our intuitive Cartesian space. Our solution, our Rosetta Stone, was the Jacobian matrix, which brilliantly translates joint speeds into hand velocity. And finally, we uncovered its secret power, this amazing duality. The Jacobian transpose does the reverse translation, mapping the forces we want at the hand back to the torques we need at the motors.
And as the source text itself says when it reveals this relationship between force and motion, it is not a coincidence that this matrix is the transpose of the Jacobian. This isn't just some lucky fluke of mathematics. It reflects a deep, fundamental principle about how physics works, showing just how tightly woven together motion and force really are. And that kind of leaves us with one last big thought to chew on. If this one, relatively simple matrix is the key that unlocks a robot's ability to both move and apply force with precision, it really makes you wonder, what other incredibly complex behaviors, from a robot learning to walk to gently grasping a fragile object, are just waiting to be unlocked by the next single, elegant piece of math? Thanks for watching.